The last section in this chapter is about looking at implicit relations, and the tricky part about implicit relations is that it's always hard to talk about a sign change when you have implicit relations. So instead of that, we're going to look at mostly the second derivative test. So a critical point is whenever your derivative either is equal to 0 or your derivative does not exist. So for these implicitly defined derivative functions, when you do the derivative, you have dy dx equals something. Often those are fractions. So you'll set your numerator equal to 0 and your denominator equal to 0 to find your critical points. So here's an example of one. We have x squared plus y squared equals 25. So to find the critical points, we're going to take the derivative. And I'm going to divide by 2 and also move the x over to the other side. So our critical point is going to happen if x is equal to 0 and if y is equal to 0. Remember that a critical point is an ordered pair. Our ordered pair is not 0, 0. Sometimes we'll have an ordered pair where x is equal to 0, and sometimes we'll have an ordered pair where y is equal to 0. So if x is equal to 0, we have 0 squared plus y squared equals 25. So that means that y is equal to plus or minus 5. So we have two critical points at 0, 5 and at 0, negative 5. And then if y is equal to 0, same thing. We have 5, 0 and negative 5, 0. If I need to determine whether I have a maximum or minimum either at a critical point, then that's going to be a second derivative question. So I'm going to look at that second derivative, negative x over y. I mean the first derivative. And I'm going to take a derivative of that. And the reason I'm taking a derivative of that is with both x and y changing, it's really hard to talk about there's a sign change at an x coordinate because both x and y are changing. So we're going to do low d high minus high d low all over the square of what's below. And here's my strong advice. Go ahead and plug in your point right after you've taken the second derivative. So we have x equals 0, y equals negative 5, and also dy dx equals 0. So we're going to plug those things in. So we have 5 over 25, which means that our curve is concave up and we have a horizontal tangent line. So we would say the minimum and the justification for that is that dy dx equals 0 and the second derivative is greater than 0. That's the second derivative test. You don't have to state that you're using the second derivative test, but you need both of these two conditions in order to use it. I would expect the College Board to be looking for this correct value in order for you to get full credit for one of these questions. You don't have to do the arithmetic, but you do need to show that you could do the arithmetic. All right, this is a big problem, and I'd recommend that you pause, try it yourself, and then come back and see my solution. Because I'm going to recommend that you solve it yourself, I'm going to go rather quickly through my solution. So the first thing I want to do is take a derivative. Oops, spoiler alert, I just told you the answer. So the first thing I'm going to do is take a derivative. All of this is product rule. There's also some chain. Again, this is product rule. And there's some chain. And then that's equal to 0 because the derivative of a constant is 0. I'm going to go ahead and factor out my dy dx's and keep those on the left. And this would be negative 3x squared y, but I'm going to move it over to the other side, so I'm going to make that positive 3x squared y minus y squared. So now is this point 1, 3? Is it even a critical point? Well, let's plug in 1 and 3. So we have 3 times 1 times 3 minus 3 squared. Oh, yep, that's equal to 0. So we have 0 over 6 minus 1, 0 over 5. So yes, it's a critical point. Not only is it a critical point, but there's a horizontal tangent line. So it qualifies for the second derivative. So I'm going to take the second derivative, and I happen to know that the second derivative is a beast. Luckily, we have points to plug in as soon as we take that derivative. So we're going to do that. I'm doing product rule again. And some chain rule. Whoa, that's low-de high. I haven't even done high-de low yet, but I know that high is equal to 0 because I've already done that. So I'm just going to say 0 there and not even worry about d low. All right, now I'm going to plug in numbers. X equals 1, y equals 3, and dy dx equals 0, so that I don't have to think through too much algebra. I'm going to try to just use numbers. So 2 times 3 is 6. And dy dx is 0, so I can stop there. That's just going to be 18. And then we have 6 minus 1 squared. I can tell that this value is positive. That's pretty much as I need to know. So I know that this value is positive. And I know that this value is 0. So 1, 3 is a minimum. I included a picture of the graph here so that you could believe it. Notice how difficult it would be to talk about a sign change because you have two different things going on. At x equals 1, you have two different parts of the curve. This is not a function. So you really want to use the second derivative test when you have implicitly defined functions. You can still find critical points and you can still find whether they're maximums and minimums, but you're going to rely much more heavily on the second derivative test. The other thing that people really struggle with implicitly defined functions is, remember, if you're trying to find a coordinate, you go back to the definition. If you're trying to find a slope, you go to dy dx. If you're trying to find concavity, you go to the second derivative. And almost any time you're going to find the second derivative, you'll have points to plug in. So plug those in as soon as you take the second derivative.